Now let us try this out for the Euler-Bernoulli beam. Remember, the governing equation for the Euler-Bernoulli beam is this, where Qx is, so for the Euler-Bernoulli beam, Qx is the transverse load, so this is Qx, and W is the vertical displacement. So if it bends into a shape like this, this is Wx, where this is the x direction. So this is the story of the Euler-Bernoulli beam. This is the governing differential equation. The operator, call it L, is Ei d4 dx4. F is equal to Qx. You can prove very easily again that this is a perfectly positive, strictly positive operator. So you can write down the variational problem right away, 0 to L, and W times Ei d4W dx4. That is your Lu comma U minus 0 to L Fu, which is QW dx. This is your variational principle. Now we are going to insist not only on del pi equal to 0, but we are going to insist on del pi E equal to 0 over each and every element. So as well we can write pi E instead of pi, which means this will have to be replaced by the elemental nodal coordinates. So for every element, x1 is the first nodal coordinate, x2 is the second nodal coordinate, assuming that we are going to use two noded beam elements. So right now, this is my variational principle. Armed with this variational principle, I am now going to form the shape function matrix, and I am going to form the B matrix, the strain displacement matrix, and I am going to follow in this case the assumed displacement method. Why it is better to follow the assumed displacement method in this case is difficult for me to explain at this moment. It will become clearer with a little bit of experience with this method. But right now, just take my word for it and just apply the assumed displacement method at this moment. Now, if you now do this procedure of applying the integration by parts to this term, we can get what we have done many times before. So let's erase this and quickly apply integration by parts. So if you do that, you have half, and then you have W. Take a derivative, take integration, one integration, so you get del cube del x cube of W times Ei at x1e x2e minus you are left with Ei d cube W dx cube and dw dx minus this term remains. I'm not doing anything to this term. I'm just working on this, on the first one, this one. Okay, let's do integration by parts once more. This remains. This will become uh, minus EI uh, dw dx times d square w dx square evaluated at x1e and x2e plus EI integration x1e x2e d square w dx square into d square w dx square dx. This is d cube w, sorry. All right. Now, once you have this, you realize that uh, this quantity EI, this quantity EI times d cube w dx cube are the bending moments, are the shear forces at the ends x1e and x2e. So EI d cube w dx cube are the shear forces, let's call them Q, and EI d square w dx square are the bending moments, let's call them M. So this follows from your Euler-Bernoulli beam theory. So once you have these two expressions, this you can see as EI times uh, Q1, Q2 W2 minus Q1 W1, and this you can see as minus of M1 M2 um, M2, and this is we can call this theta, because this is the derivative of the vertical displacement, which we call theta. So this is M2 theta 2 minus M1 theta 1. So these two terms can be written in this manner. Now we are going to use a generalized force, and we are going to call the Q's at the nodes, at the forces and the moments at the nodes, both as Q. So we are going to replace this by, so Q1 is a shear force, Q2 is a bending moment, which is M1, Q3 is a shear force, Q4 is a bending moment. So this is used in place of Q1, M1, Q2, M2. So we are going to use Q's at the nodes for both bending moment and shear force. So if we do that, then we can write this whole thing as this. So this is what we are going to write. Again, you see that the natural boundary conditions come out of it. Of course, at the ends, the displacements might be zero, then these two terms are zero. At the ends, the rotations might be zero. This is theta 1, this is theta 2. These might be zero, then these two terms are zero. But at the same time, Q1e, Q2e, Q4e, Q3e might be specified as well. So these are natural boundary conditions, whereas specifying these are essential boundary conditions. So now we have the entire variational statement for an element, and we are going to now take del pi e equal to 0, and that will be the starting point of our finite element formulation. But for the finite element formulation to succeed, we now need the shape functions and the strain displacement matrices. So what do the shape functions do? The shape functions connect the nodal degrees of freedom to the value of the degree of freedom at any point. That means if the value of the degrees of freedom, there are two degrees of freedom. So the degrees of freedom are Wx and theta x. These are the degrees of freedom, and we should have the n matrix connecting it to the nodal displacements, which are W1 theta 1, W2 theta 2. These are the nodal degrees of freedom, and n has to connect it to the vertical displacement and the rotation at any point in the element. So to do that, what we are going to do is we are going to assume now a WH which has this form. Remember, our variational principle contains this term. So if you take anything lower than second order polynomial for W, then this is going to go to 0. This is going to go to 0, so you are going to lose the energy that's contributed by this term. So we have taken a third order polynomial. Now we are using this assumed displacement method here, because we now have two nodes, but we now have two nodes but we are not using linear shape functions, we are using something more than that. So that is allowed, that can be done easily if we use the assumed displacement method. So now at node 1, I have WH at node 1 is, let's say, is W1, dWH dx at node 1 is equal to theta 1, and WH at node 2 is equal to theta 2, is equal to W2, and dWH dH at theta 2 dx at theta 2 at x2 is equal to theta 2. Sorry. So that's what I have done. W1 theta 1, W2 theta 2. This first equation is for W1 from here. The second equation is a derivative, first derivative of this, and this gives theta 1, similarly theta 2 and W2 and theta 2. Now this can be inverted, so I can call this the A matrix like before, and I can call this my A matrix, which contains these unknown coefficients. So I can write A equal to A inverse of this, which I call W, modal variables A inverse U, provided A is invertible. And when I do that, I get the connection between so WH x is 1x x square x3 times the A vector, and therefore when I have done this inversion, I'll get 1x x square x cube times A inverse W. So this whole thing becomes my shape function. Now this inversion is, as you can see, it's a 4x4 matrix. Inversion is not that easy, and but it's still invertible. You can still invert it, and if we invert it, then we will get WH in the form of N1, N2, N3, N4, where I have done the inversion on Maple, and the inverted functions are these. So these are the shape functions for this problem derived from the assumed displacement method, and you can easily see that they are not linear functions, though we have two nodes at the two ends, but these are not linear functions. These are cubic functions, and this is an example of cubic spline interpolation. However, they still satisfy the Kronecker delta property. They still have to satisfy the Kronecker delta property, but they are not linear functions. Now it's easy to see that they satisfy the Kronecker delta property, because if you put x equal to x1e in this, these terms go to 0, this term goes to 0, and you are left with 1. So that n1 at the location of node 1 is 1. And also if you put say x2 here, or if you put, let's erase this. If you put x2 here, then this becomes LE, this becomes LE, so this becomes minus 3 plus 2, that's minus 1, 1 minus 1 equal to 0. So at the location of node 2, this is 0. So Kronecker delta property, you can check that out for the others. So Kronecker delta property is satisfied for all cases, all shape functions, but these are not linear shape functions. So, and that is because we got them from the assumed displacement method. Now the remaining process is quite similar. So we write WH as n times u. So n is the matrix that is connecting the displacements, the vertical displacement at any point inside the element to the nodal displacements. In this case, remember the nodal displacements are two vertical displacements and two rotations. So it's connecting all of them. So it's a kind of a generalized displacement connecting them to the vertical displacement at one point, and then del square WH del x square d square WH dx square gives you the strain in this case, and this is connected to u, the nodal displacements, through the strain displacement matrix. So once you know this, that's what you do from here, from this expression. You can take its derivative twice. We have already made sure that that derivative doesn't go to 0 from here. So we can take this derivative twice and plug it in to so that derivative will contain w1 theta 1 w2 theta 2, that is it will contain capital U, and we can get the B matrix easily. So this is your shape function matrix. You can get the B matrix by its derivation. Then go ahead and form del pi E. Easy in this case. You take del pi E from here. So this term will give you 2 times d square W dx square delta of d square W dx square. And this will be same as d square delta W by dx square. So that's the first term. This term will simply give you q times W. These will lead to q1e times delta W at x1e. This will lead to delta W at x2e times q2e. This will lead to d del W del x at x1e q4e, and so for the last term you can figure that out. And this is what we get. This is what del pi E is. Okay, now what remains is you plug in this discretization here. So del WH is n del U, and you may want to write it as del U transpose n transpose as well. So when you write it like this will become del U transpose n transpose Q. You write this as so write this first, del U transpose B transpose, and then write this as du. Again, del U transpose is there in the first term and here in the second term. So your K matrix will now become del U transpose will come out, and then you will have B transpose. Put the EI in between, it's a scalar, B dx, and U can also be taken out of the integral. So this guy will now become your KE, the local stiffness matrix. Here in the second term you have n transpose Q integrated from x1e to x2e dx as your Fe, and these are boundary terms. So this is what you will have. So this is your Ke and this is your Fe. And I can now evaluate Ke. I leave that to you. You can now evaluate Ke. So to do that, take this n, take two derivatives of this, find the B, find B transpose B, and when you find B transpose B, you can get the Ke matrix. And the Ke matrix again will turn out to be exactly the same as your what we had got before. And Fe has a contribution from the distributed load, which we did not have before, because in the early part of the course we had formulated it without the distributed load. So this is the consistent distributed load, consistent nodal equivalent of the distributed loads. And then Q1, Q2, Q3, Q4 can be specified. Those come from the boundary terms. So del W1, del W2, W3 and W4, they constitute, sorry, this is del W1, del W2, this is theta 1, del theta 1, del theta 2. So this part you can write as del U transpose, these are, which is equal to del W1, del W2, or we can write it as del W1, del theta 1, del W2, del theta 2. We can write it like this, del U transpose. And then I have Q1, Q2, this should be Q3, I'm sorry, this should be Q3 and Q4. So what you have in these boundary terms is basically del U transpose times Q1, Q2, Q3, Q4. So this term gives rise to the stiffness matrix. This time gives rise to the first term in the force vector. And these entire terms are due to the presence of shear forces or bending moments at the ends of the element. If there are shear forces and bending moments applied at the ends of the elements, then these will be non-zero. So, so these two contributions to the force.